All right, let's dive into a pretty deep and fascinating topic today. We're going to take a look at the mathematical underpinnings of a very specific cosmological model, one that imagines a universe that could be eternal, cyclical, and, yeah, completely self-supporting.
So let's start with a really provocative question. We're all used to thinking of the Big Bang as the absolute beginning of everything, point zero. But what if it wasn't? What if the Big Bang was more like a reset button, the end of one universe and the start of the next, just one moment in a never-ending cycle? That's the core idea we're going to unpack here.
To even start building a model like this, you have to begin with a really radical idea. You have to stop thinking about the universe as mostly empty space with stuff in it, and instead see it as a single continuous medium, a kind of dielectric superfluid matrix that is the fabric of reality itself.
And look, this isn't just some poetic metaphor. The model gets down to brass tacks, using the serious mathematics of fluid dynamics and electromagnetic theory. The idea is that by using these tools, you can describe not just how particles bump into each other, but the fundamental, fluid-like behavior of spacetime itself.
Okay, so what you're seeing here is really the bedrock of the whole model. The first equation is about continuity. It basically says our cosmic fluid doesn't just appear or disappear, it's conserved. The second one deals with the conservation of momentum. It describes how this fluid actually moves and reacts under all the different pressures and gravitational forces. These are the rules of the road.
So, now that we have the basic rules for our fluid universe, we've got to ask, what actually makes it go? What are the forces at play? Well, it all comes down to this constant cosmic tug of war between two opposing forces, compression and expansion.
Now, the expansion part is really interesting. The model proposes that it's driven by neutron decay. This process creates hydrogen and basically generates this outward push on the spacetime fluid. But, and this is key, it's not happening the same everywhere. The strength of this push depends on the local density, a relationship the math geeks call alpha of rho.
And this is what that looks like in equation form. That delta V term, that's the rate the volume is changing. And you can see it's directly tied to that alpha of rho, the density function. So what does that mean? Well, in really low-density places, like those giant cosmic voids, this expansionary push is the main game in town.
So what's stopping this outward push from just, tearing everything apart forever? Well, it's the force we all know and love, gravity. While neutron decay is busy pushing the voids apart, gravity is doing the exact opposite. It's pulling matter together, compressing that cosmic fluid into super high-density regions, like what you'd find around event horizons.
And here is where it all comes together in one elegant package, the integrated fluid gravity equation. You can literally see the balance right here. The terms on one side that represent gravity trying to make everything collapse are being fought to a standstill by that alpha of rho expansion term. It creates this beautiful dynamic equilibrium, which means the universe doesn't fly apart, but it also doesn't just crunch back into nothingness.
So where does this cosmic balancing act take place? The model theorizes a pretty wild structure called Shirley's surface. Think of it like a Mobius strip on a cosmic scale. It's a continuous single-sided surface that actually connects regions of matter and antimatter. It's the bridge where the gravitational crunch in one area is thought to actually fuel the expansion in the other, keeping the whole cycle going.
Okay, so we've got the dynamics down. Now let's dig a little deeper into the nature of space-time itself. If it's a fluid, what kind of fluid is it? The model proposes it acts like a superfluid, and that has some absolutely huge consequences for one of the most fundamental constants of nature, electric charge.
This quote just nails the idea perfectly. It's saying that the reason electric charge comes in those neat little packets, quantized, is for the very same reason that flow in a superfluid is quantized. It's not some random rule, it's a direct result of the weird, loopy geometry, the topology of space-time itself.
And this isn't just some loosey-goosey analogy. I mean, look at the math on the screen. On the left, that's the integral for fluid circulation, which has to pop out in whole number units. On the right, that's Gauss's law for electric flux. The argument here is that these equations aren't just similar, they're describing the exact same fundamental topological rule.
This table is basically the translation key. It maps the ideas from one field to the other. The velocity of the superfluid, that's like the E field in cosmology. A quantized vortex? Well, that's your quantized charge. A vortex is basically a defect in the fluid's flow, right? This model says that's topologically the same thing as a source or a sink, a charge. It's all just a consequence of spacetime having these superfluid properties.
So here's the absolute punchline. The reason charge is quantized has nothing to do with forces or interactions, the dynamics. It's pure geometry. It's topology. The very shape of the universe makes it impossible for something like half a charge to exist. In the same way, you can't have half a hole in a donut. The shape just doesn't allow it.
All right, we have our fluid, we have its rules, but for a cycle, you need a reset. You need an engine to turn things over. And in this cosmology, that engine is the black hole. But not as an endpoint, it's a transformation point.
So how does that work? This idea hinges on something called the Haggard-Rovelli solution. It suggests that singularities, those points of infinite density, don't actually form. Instead, when matter gets squeezed down to the absolute limit, to Planck density, quantum gravity effects kick in and create this insane outward pressure that forces everything to bounce back out. This diagram walks you through it. Look at the bottom. That's matter collapsing inward. But instead of hitting a dead end, it enters that fuzzy bit in the middle, a finite quantum tunneling region. In there, the classical rules don't apply. And what comes out the other side, at the top? A white hole, with all that matter exploding outwards. And the crazy thing is, this whole process works with Einstein's equations everywhere except for that one tiny little quantum bounce.
And here's where your brain might start to melt a little bit. For an observer falling in with that matter, the bounce might happen incredibly fast. But for us, watching safely from far away, that immense gravity causes extreme time dilation. It would stretch that bounce out over billions, maybe even trillions of years. So what we see as a stable astrophysical black hole could actually be a star that's in the middle of a bounce, just playing out in the ultimate slow motion.
So, we've gone through the fluid dynamics, the weird topological properties, and the quantum engine of this whole thing. Now, let's put it all together and see how it creates a single, coherent, self-supporting system. So here's the whole picture, the complete loop. You've got the universe as a continuous fluid. It's held in a perfect balance by the push of expansion and the pull of gravity. The very fabric of this fluid has superfluid properties, which is why charge comes in discrete packets. And finally, black holes aren't cosmic dead ends. They're the quantum engines that take all that compressed matter and recycle it, resetting the whole cycle. It's a completely closed loop. Which, of course, leaves us with one last absolutely staggering thought. If a model like this is even remotely on the right track, then our entire universe isn't a one-time event. It's just the latest chapter in a book with an infinite number of pages. Which forces you to ask the ultimate question. If there was no true beginning, what did the universe that came before ours even look like? It's a question that completely reframes our place in a cosmos that might just be truly, beautifully eternal.